All right, it's just after 11, so I think we'll get started. Good morning, everyone, and thank you so much for joining us this morning. I hope you can all see right now on your screen a presentation slide that says a new approach to meat quality and safety. If you can't, please send me a message in the chat, which you can find along the bottom of your screen. Unfortunately, we do have everyone on mute because we have so many folks on the call today. Well, if I could just ask you to pull up our agenda, we'll just really quickly go through that. I'll introduce myself first. I'm Heather Galt. I'm the Vice President of Marketing here at P&P Optica, and I will be your host for today, but you won't hear from me very much. We're going to spend most of our time going through the agenda, which hopefully you can all see on your screen. So we're going to start off by covering a little bit about the generalities of inspection and understanding inspections. I think that's a really important place for us to start, is having some common language around how do we understand an inspection system. Then we'll spend some time learning about vision systems broadly, so not just focusing on PPO and our smart imaging system, but more broadly on vision systems and how we can understand them, getting into some specifics. And then we'll talk a little bit about automation and how vision systems can help automate and how they fit into the broader context in the plant. In terms of Q&A, if you do have questions, you're welcome to send them in anytime. So you can see down the bottom, there is a Q&A button. So if you just click on that, you can type your question in. They will pop up throughout the presentation, so I'll see them come in. Because we are fairly tight with our content, we have quite a bit to cover. We're going to do that first, and then we'll have a Q&A moderated at the end. So we'll make sure your questions get covered at that point during the presentation. Well, if you can, yeah, you've got the pull out for the housekeeping items. So we've talked about Q&A. If you do want to chat with the whole group, feel free to use that chat function. And I do want to make sure that everyone's aware that the seminar today is being recorded. If you are hoping to be able to watch it again later or share it with your colleagues, we will be posting it on the PPO website in the resources section. So that should be available within the next 24 hours, and you're welcome to share this with your colleagues anytime. So with that, I'll introduce our two speakers. The first one is Olga Pawluczyk, the CEO here at P&P Optica. And our other speaker is Dr. David Gilbank, who is the data quality lead at PPO. So between the two of them today, we've got the two best experts to talk to you about vision systems. And with that, I will turn it over to Olga to get us started.
Thank you, Heather. So thank you very much, everyone, for joining us. And I hope that this presentation is somewhat instructional and useful for you. Right now, detection systems, especially in food processing, are, I would say, very capable, but we don't have very good language to speak about them. And we thought that we would make this presentation for you in food processing to maybe try to bring you to some of the language that we in image processing and data analytics use. So right now, I didn't want to use the worst thing that's happening right now, so COVID, but consider the test for a common cold. And in a perfect world, all sick people, if we were testing them with some sort of diagnostic test, all sick people would test positive. All positive tests only would correspond to the sick people. Healthy people would test negative, and all negative tests would only correspond to all the healthy people. But unfortunately, no test available right now is 100% perfect. So we often get sick people who test negative, so they spread disease, and then healthy people who test positive, so that it starts fear and maybe unnecessarily limits the ability of healthy people to participate. Same, and can you design a test that would return only 100% positive results? Yes, you can, but it actually wouldn't be that great, because you could still diagnose healthy people as positive, and it wouldn't be very useful, right? So even though you have 100% detection of positive results, you might make mistakes that things that are not positive are read as positives. And that's called false positive. And the flip side is also available for negative results. So what if you wanted to say, we want to be 100% right on all negative results? Well, yes, but what if you then classify sick people as negative? So you get a false negative. And in detection, in plant detection or detection of foreign objects, a positive event really means that there is no object to detect. A negative event means that there is no object that is to be found. And you have true positives, which are correct detections, and false positive, which are the incorrect detections. So essentially, you think there is something found, but there is nothing, so you have a false rejection. True negatives would correspond to something like correctly identifying clean objects. So frankly, most product in your factories is a true negative, but a false negative would be something is identified as clean, but there's actually a contaminant present. So, the true positive and true negatives are very easy to understand, but it's actually the presence of false positives and false negatives that makes detection methodology that challenging, because you have to balance how well you detect something and when do you make mistakes, and the mistakes will be made on any detection methodology. So effective detection systems must have both true positive and low false positive rates. The interesting part is that human factors come in even at the design of a detection system. So how humans think and what we pay attention to dictates how a detection system is designed. The big problem in a lot of discussion on detection systems is that many of the studies that are conducted in a factory setting, in a plant setting, are actually very difficult to design properly. It is very easy to find true positives. So you define you find a positive, you look at it, yes, there is a foreign object, or yes, there is a detection. So you're very happy that this is that your detection system is working. The problem is it's very difficult to find true negatives, as in, is there a foreign object, and there is no foreign object present, and I say there is no foreign object present, but what if there is an object present and I didn't flag it? So that is almost impossible to determine in factory settings. And so how do you design a test to actually test and measure all of these aspects? The only way you can test a detection system is by essentially running an experiment through it. You have to know exactly how many foreign objects you have. You have to then run all those foreign objects through a system, and then you can measure what was found, what wasn't, what was identified, what was not identified. And I think that's something that's sometimes missed in rush to determine whether a detection system is working. But doing that experiment, actually taking a couple of hours to run the experiment on a very well-known representative sample, is hugely important to be able to compare different detection methodologies in your plants. So just to give you an idea, what does this look like in a normal plant? Well, true positives or presence of foreign objects happens very rarely, maybe, less than 1% of the time. So in this case, if we had 1% of foreign objects present, we had 97% of no issues whatsoever. So clean product is identified as clean product. That's all great. But what if we have just a few little false rejections or missed foreign objects? It's actually, if you look at how sensitivity of a system works, this means that sensitivity of your detection system drops dramatically, even if you have one single missed foreign object. And that's, again, that those measures of sensitivity and specificity become extremely important in how detection systems can be analyzed. And knowing this math for each of your systems becomes important in knowing how well you can trust a detection system installed in a plant. So what is really detection is not are you finding objects, but it's the probability of finding an object. And it's dictated by configuration of the detection system, the detector itself, so resolution, noise, and speed of acquisition, but also the environment in which the detection system is working. So for example, heat typically makes detectors more noisy and less specific. And then the background. So what is the material that you're looking for foreign objects on? Is it complex? Is it uniform? Is it thin? Is it thick? Does it have very complex surface structure, or is it flat? And then also the object itself will really dictate how well it's easy to find. So for example, trying to find a piece of white plastic on a very light background will be much more difficult than finding black plastic on the same light background, even if they're the same size, the same chemical composition other than color. The other aspect of detection is that distribution of the sizes and aspects of objects that you find in your plant actually varies, and it varies with types of objects. So you might be able to find very few metal pieces, and you always have very few metal pieces in the plant, but you have very high concentration of mid-sized plastic pieces or something like that. So the distribution of how often you're expecting to find an object also dictates how to select the best detection method. So if you only see few metal pieces a year and you know that that's the baseline, do you really need a metal detector? Well, yes, because you have to find those, but maybe your metal detector just has to find very specific sizes and you don't really have to worry about it too much. But if you have huge distribution of wood pieces, you might need to work on what kind of detection method would actually help with the wood detection. And the final aspect of kind of just detection in plants is human inspectors. And I think a lot of us, fall back on human inspection as the next optimal solution. They're already in the plants, and humans, can see a tiny speck of something. The problem is humans. One drawback of humans is that they tire over time, and their vigilance or ability to look at a foreign object and actually say there is a foreign object there falls dramatically with time. And I think that's something that we don't think about very often, especially in plant conditions where it's noisy and cold and uncomfortable and other things are going on. We expect our human inspectors to perform perfectly at all times, and unfortunately they're not. So one thing that automatic inspection systems add is that the curve of vigilance that you see on this slide is really flattened. And even if automatic detection systems don't detect as small objects or are not as great as a rested human, over time at least you can depend that their vigilance will be constant, and therefore you will have much higher chances of finding all foreign objects or foreign objects that do enter your stream. So paying attention to how you train human inspectors, if you don't have any other solutions, but how do you train them? How do you pace? How do you make sure that they continue being vigilant? And how do you reward vigilance are very important aspects to think about if you're using human inspectors. That was a little bit about talking on about the system itself and detection itself, but what are vision systems? Because this is really why you're here. So vision systems typically require some sort of source of energy that interacts with an object, is then detected by a detector and displayed. So your eyes are actually a vision system. A camera on your iPhone is actually a vision system. Automation and automated vision systems have one much more significant component, and it is automatic decision making. So instead of just displaying something, the automated vision system has to find and define any problem or any object that you're interested in. And that is the key challenge in many automated vision systems. So this is a slide just to show you that there are many, many different types of vision or sources of energy that can be used. And depending on the energy that's being used in a detection system, you see different aspects of your product. And this is an example of, from medicine and from food. Different types of vision systems. So on the top row, I'm showing different images formed depending on what type of energy you're using, from X-ray to microwave. And on the bottom, I'm showing image systems that involve more than just looking at detected energies, but have to somehow transform that signal into useful information. So magnetic resonance imaging, for example, excites water molecules, and you're imaging actually how water molecules respond and not a direct energy source. So as we talk to a lot of our friends in the food processing industry, we have seen some imaging pitfalls and mistakes that people might not quite understand as they try to evaluate imaging or automated detection systems. And what this page tries to show is that the pixel size, or the smallest element of detection that your detector is capable of, doesn't necessarily dictate the smallest object you can see. So if you have a perfectly presented objects that are very high contrast on a very uniform background, so your product is, emulsified, thinned down in uniform thickness, detection of an object is relatively simple, and the detector will see it. The moment you start introducing noise of contrast or environmental impacts, or even the fact that your background or your product is non-uniform, has levels of thickness or texture on the surface, finding an object becomes much more difficult, not only for the human eye, but also for automated products. So when you do ask us about vision systems, I think kind of having an idea that resolution and pixel sizes don't actually tell you the whole story about what is detectable, and that probability of detection changes with object size or object composition is important. So when you're trying to compare detection system, it's better to talk about the probability detection curves as opposed to finite, hey, can you detect 0.5 millimeter object? Because you know what? Yeah, it's possible to find a half a millimeter object if all conditions are perfect. But in a standard processing plant, nothing is perfect. And therefore, the perfect number that we give you will most likely not be the number that you get in actual operations. The other thing that I would encourage you to ask all your suppliers, including PPO, is to ask us, what is our sensitivity and specificity? And this, again, a detector could detect 100% of foreign objects, and I could claim, we'll detect everything that goes through. But I might not tell you that, but I will reject 100% of your product. It is, in one sense, a perfect detector, but it's a detector that has completely zero usefulness online. So talking about sensitivity and specificity forces us, the detector companies, to tell you, what are your chances of finding something? What does this look like in non-perfect world? So there is a much larger and much deeper discussion that has to happen between a supplier and a user of a detector system than just asking what's the minimum size you can find. So at this stage, I will pass this to Dr. Gilbank. He will be able to tell you a little bit more about comparing vision systems and how our hyperspectral imaging works. And I'll come back to you to talk a little bit more about other applications of detections and vision systems and maybe answer any questions. So David?
Okay, thanks, Ola. Can you hear me okay? Is that great? Okay, so let me just check I can share my presentation. Is my presentation coming up? Sorry, give me a second. Oh, sorry, have you stopped sharing, Ola? It says I can't share while you're still sharing. Sorry, just give me a second. Present.
I have unshared.
Share. Okay, here we go. Okay, so this one. Okay, perfect. I think, is that showing up okay? Yeah, great, thanks. Okay, so as Ola said, I'm going to talk a little bit about comparing vision systems. So I'm going to go through the three main flavors or types of vision systems, if you like, that are available. So these are the ones that I've grouped into categories. So the first I'm calling traditional vision system, and hopefully by the end of this I'll have explained a bit why the kind of umbrella term for vision systems really sort of does at least two of these three technologies kind of a disservice. And then I'm also going to talk about multispectral imaging, which is also becoming fairly widespread, and hyperspectral imaging, which is also a very high-tech emerging technology, and that's what we use. So before I do this, I've got to give you one last piece of background in addition to what Ola's already mentioned, and you'll notice that both these two techniques contain spectral in the title, so I'm going to have to talk a little bit about what this means, a little bit about what spectroscopy is. So if you think back to maybe high school physics, you've probably all done an experiment that looks a little bit like this. So if you take a light source, say the sun or a lamp, and let the light from that fall through a prism, you know that this gets split up into all the colors of the rainbow. So this is what we call a spectrum. And then this is light. You can see this rainbow, this spectrum with your eye. And as Ola mentioned earlier, there are lots of other wavelengths, lots of other types of light as well beyond just the visible light, which is what you see with your eye. So in fact, near-infrared radiation was first discovered a couple of hundred years ago by a scientist who placed a thermometer just outside of the red wavelength that he could see with his eye here, and noticed that when he split the light up, the temperature actually went up here. So he could detect that there was some other radiation there that he couldn't actually see. And so that also ties back to the pictures Ola was showing earlier, kind of, you remember like these thermal imaging cameras where you see the heat from a body. That's essentially what near-infrared is. And so I'm going to talk mostly, so visible and the near-infrared light or wavelength is something that's going to come up a little bit throughout this section. So the way that this technology works for spectroscopy, so in the case of the two later technologies, we use a light source in the same way we use specific light bulb, lamps, but you can think of this as just a regular bulb. We shine this onto the product that we're interested in. In this case, this little cartoon here is just showing you some chicken, or it can be whatever you've got on your assembly line, on your production line. The light bounces off that and then gets split up by the prism and then is recorded by a camera at this end. So as Ola showed in one of the earlier graphics, when the light bounces off, it's actually changed. Some of it's absorbed, some of it's reflected. So it's changed depending on what material it's bouncing off. So to show you what this looks like, so this is just the same graphic again at the top. So the different colors of light, or the different energies of light, as they interact with the material that you're looking at here, some of the energies are absorbed depending on what the molecules, depending on what the chemistry is within the material. And by looking at what light is missing when you look at this spectrum at the end, what's been absorbed into the material, you can actually identify what's going on in the material under investigation. So this is actually a really powerful technique for looking at what we call the chemical fingerprints, for identifying exactly what's inside the product that you're looking at. Okay, so coming back to the idea of how this works with vision systems. Sorry, my next plot. Okay, so This is probably a picture that you're familiar with. You've got some sort of conveyor belt on your factory line. This is our system testing some product in a tray. It's actually ground pork in this case. It doesn't really matter. But you notice that there's a line across here, a line of light. So this is actually where we're shining our light to illuminate it to be looked at by the equipment at the other end. So this is just showing you that what typically happens in all these vision systems, because although they differ in several respects, one thing that's common to all of them is the way in which they collect the data in the first place. So you basically shine a line of light across this, and the camera itself is recording an image in this line as well. So what happens is you can think of the camera, it can be as simple as a traditional vision system, just like the camera you have in your cell phone at home. But the main difference is that you only image a single line at once. And the reason for doing this is because the movement of the belt actually gives you the second dimension of the image. So you have information, you take your picture in one line across here in what I'll call the spatial direction. So I'll refer to this a few times, but this just means the width across the belt. So you can see what's going on at any point in this line. And as the conveyor moves underneath this, it rolls past and you start to record all these lines together. They build up a 2D image, like the kind of thing that your cell phone would record. So this is one of the ways in which all three of these systems are similar, the way that they build up these images, but they differ in the type of data that they gather, which I'll get onto in a moment, and then what we can actually learn from this data, the amount of the wealth of information that comes from the specific technology that's been used. Okay, so for this setup, for the following slides, I'm going to show you the same thing for all three different types of system. And so what I'm showing you here is this is just a picture of kind of our experimental setup. So this is 5 pieces of chicken, can be any meat, doesn't matter, or any product in fact, all on a background of conveyor belt. And so the 4 outer pieces, you can see quite easily here and possibly here, but maybe a little bit more difficulty here and here. There are actually 4 different types of common foreign materials on this, bits of like blue plastic, cog rubber, bits of bone, various different things, and the middle piece of chicken is clean. So ideally what you'd want, so this is showing kind of a real world view of how the experiment's set up. So what I'm going to show you is how the 3 different types of vision system see this, the side of information that you get for it. So in an ideal world, probably what you'd like to have is something which tells you where all the foreign objects are, and if it's important to you, what type they are. So I'll get into that in a little bit more in a few moments. So the simplest and kind of most familiar, the easiest to start with, is the traditional vision system, or what I'm calling the camera-based system. So in this case, the picture that you see from the camera is essentially exactly the same as the picture I've shown you of the experimental setup. And this is just because it's just using a regular color camera. So what you see here is essentially what the vision system, what the camera-based system sees. So in the following slides, I'm going to show you what the vision system sees. And I'm going to show you kind of these little plots here. So all of these, what they're showing you is the different colors or different wavelengths of light that across the bottom that the system is sensitive to, and then how intense or how bright the light that's reflected off the system is here. So if you've ever looked inside a camera or a modern digital camera, or if you ever look closely at a TV screen, you'll see that the pixels are actually made up of 3 different colored elements, a red, a green, and a blue. And by varying the intensities of light, you can make all the colors in this. So for example, if you had 0 light or very low intensity in all the red, green, and blue, you'd see black. The light that we're shining on this in the first place is essentially white light. So it starts off as essentially all blue, all green, and all red, full intensity. And then, as I said in the earlier slide, the properties of the material absorbing the different wavelengths give you what you see out the other end. And in the case of the vision system, basically all you see is that chicken is relatively pink. It doesn't give you much more detail than that. So you see that you've got a bit more red light than you have in the other 2 bands, and that's essentially it. And so this doesn't give you much information in terms of the colors that you're looking at, but if all you care about is I've got brightly colored bits of conveyor belt or anything, any product that's going to get, any product that I'm worried about contaminating, sorry, any parts in the factory that I'm worried about contaminating my product is brightly colored, like fluorescent orange, for example, and very different from the color of the product, then this may be exactly what you need for your system. It's a simple thing. It's very good at finding things that are very different colors. But if you look at things like, in this case, there's some sort of a slightly transparent plastic, or there's some white plastic here, which is very similar in color to the chicken. And also keep in mind that this is sort of what human inspectors would see as well, because they're looking in visible light. Then it can get very hard to see some of these products. To see some of these contaminants. So in that case, you might need something that's a bit more sensitive in terms of the color that it can return than just a pure vision system. So the first of the two kind of spectral systems is multispectral imaging. So in this case, so we've got again the original setup. This is what you're looking at, 5 pieces of chicken. Now this is how the multispectral imaging system views the data. So there's a couple of things to notice here. So first of all, the colors here have been color coded. They all look very different from the colors that we were seeing in just the visible light image. And I've done this to illustrate that typically the old camera-based systems work in visible light, but the spectral systems can work in either visible light or near infrared, which that's also relatively common. And so a lot of the things that we care about in food production, so a lot of things like meat and organic compounds actually have much stronger spectral signatures, much stronger chemical fingerprints in the near infrared. And so it can be useful to use that rather than visible light to get a better picture of what's going on. So this is what I'm showing you in kind of this false color here. The other factor you'll notice is that there's these stripes, there's these missing bits of data across the image. And this is because that if we go back to this picture that I've got here, the way that multispectral imaging works, and I won't go too much into the detail of the technology, but there's a very good article on Wikipedia you can look up if you're interested in how this works. So multispectral actually doesn't take an image of the whole line at once. It actually has to scan through the different colors at different points of the line. And so what this means is that you actually miss some spatial information, so you have gaps in your data. The advantage of multispectral imaging in terms of color information that it returns over the traditional camera that we just looked at, the 3 different colors, is that it can return many different colors. So typically you get something like 5 to 10 different bands, different colors that it can look at, and you can tune these to be more sensitive to the specific chemical fingerprints that you care about in your product. The disadvantage is that you have to decide on what these bands, what these colors are, these wavelengths ahead of time when you build the system. So the manufacturer that's building this will run some experiments and find that this works well for specific types of plastic, for example, and then custom design it to return information here and here, for example, where there's strong signatures of plastic. But you're kind of fixed to that. Once you've bought the system, those are the wavelengths that it returns, and that dictates what product or what contaminants it's sensitive to. So in this case, you can see this is detected. These labeled with FM here are the 2 foreign materials that it's found. So these 2 out of the 4. So one of them here happens to actually fall on one of these gaps in the imaging line, so it missed it simply because it's not 100% coverage in the spatial information. And the other one it's missed because it's a type of material that it wasn't trained for, and these wavelengths, these bands just aren't sensitive to that. So that's kind of the downside of multispectral imaging. It's an improvement in terms of the number of colors and the details that it can return over traditional vision systems, but it doesn't return complete information. There are gaps in the information that it returns. So the final of the 3 types is hyperspectral imaging. And so in this case, so same deal here, I've color coded what the image is here. So this is showing that it's not necessarily using visible light, it's using near infrared, which is more sensitive to the transitions, to the absorption features that we care about. In this case, you can see the different color coded foreign materials have all been found. So you'll also notice that there's a key down here, which I'll get to in a moment, which is identifying exactly what type of material this is. So the main thing you'll notice is that we now have complete spatial coverage. It's imaging every single pixel as it rolls past on the conveyor belt. We don't have these gaps like you do with the multispectral technology. And the other thing that you'll notice here is that instead of having just 3 separate colors or 5 separate colors with gaps in it, you have this complete continuous coverage. So actually, if you look very closely, these are all separate bar charts, the same as they were in the previous ones, but there's actually over 500 lines here. So this is actually data from our system showing that you can actually detect 500 very, very narrow color channels. And this is important because it means that you're very sensitive to small differences in the shape of the absorption from the different chemicals that you've got here. The other thing is that this means that you can feed into the model the signatures, the different spectra of the different types of materials, and the data is so rich that you can actually go in and measure the difference between them to identify what the material is in real time. So this is important, for example, if you're trying to root cause a failure in the factory. So if you suddenly notice that you're detecting lots of things that have come up as white rubber, say you've got a rubber cog somewhere in your system, and suddenly you see a whole shower of particles that you didn't see before, which all come up as white rubber, you know that somewhere upstream you've had a failure with the cog, so you can actually go back and fix it almost in real time. You can see exactly where the failure is coming from. So that's one of the advantages of having this wealth of detail, that you can actually identify in real time the specific types of contaminants that you're getting. So here I'm just showing the same information again without the coloring underneath. So this is just showing spectra again. So here, so just look at the orange line for now. This is essentially the same as I just showed. This is what chicken looks like. So this is pointing to chicken. In this case, this is pointing to the white rubber. So this is a very, very different chemical signature. This is showing, you can see these sort of two characteristic absorption features here, which show you exactly what type of material this is. And it looks very different from the chicken. So this is sort of just illustrating what I just said, that you can in real time identify what material it is. You can build up a library of the different materials and recognize their chemical signatures. You can also, aside from this, recognize things that you haven't seen before, that you haven't trained on. So data that just doesn't look like chicken. It may not look exactly like white rubber, but it looks different enough that you can tell that you've got some sort of foreign contaminant there. The second thing that you can do with this incredibly rich data set is you can see this is actually just looking at chicken in two different places on the same breast in this case. So you can see that you can measure very, very small differences that wouldn't be possible with the earlier techniques, where you've got these very broad color bins, these very crude representations of the color, and you can see very, very small differences between it. So you can actually feed this kind of information through the machine learning models that we have, the artificial intelligence, and you can do various other things at the same time as detecting foreign materials, if that's something you care about. So you can do things like looking at the tenderness of the meat, or looking at fat lean composition, or other things that require this very, very fine detail, this kind of exquisite resolution that you can get with spectroscopy, with these many, many color bins here. So this, in fact, is showing two different pieces of chicken. This is exactly two different areas of chicken. This is exactly the signature that you get if one piece of the chicken was more tender than the others. So this is also something that this technology allows you to do. So kind of just in summary, I won't go through this in a lot of detail. I think Olga will bring this up again, and you can always pause this on the playback afterwards. But just to summarize the main difference between the vision systems. So hopefully I've showed you that vision to me means what you see. So vision, I always think of, this is what you see with your eyes. I think of visible light. I think of 2D pictures like I showed at the beginning. And I think this is why this is kind of somewhat disingenuous to lump everything under this umbrella category. The detail that you get with multispectral or hyperspectral imaging is really very different from what the image vision conjures up to me. So just to compare the main differences. So the number of light bands that you get, typically your entire region that you're looking at would be only 3 if you're looking with a traditional vision system, your typical red, green, blue. Multispectral imaging, you get a bit more detail, more bands. But with hyperspectral imaging, you get your whole wavelength range gets split into hundreds or thousands of bands, so you can get this really exquisite detail. This is sort of what I've just hinted at in the previous sentence. So with all these extra bands, they can be finer. You can see much, much finer details in the chemical signatures, in the colors of the data that you're looking at, and that allows you to do the things that I just mentioned in the previous slide. This means you get much, much more information from the more detailed spectra. With vision systems, basically, as I said, you restrict it to finding things that look like lumps or blobs, and maybe high contrast objects, very different things. And if that's all you need to find, that's fine. With the kind of spectral side of things, you can identify more and more chemistry, the more detail that you have, and you can identify contaminants in real time. And finally, so this is sort of what's hinted at, and I think Heather mentioned this is going to be the topic of the webinar, the next webinar coming up. The more information you have, the more you can train to do things in future. So for example, as I said, the system, hyperspectral imaging, you can, depending on what you do with the software, you can recognize things as foreign, even if the system has never seen it before. But the added advantage of this is that since you're recording all this data in line in the factory, you can go back after the fact and say, oh, I found this before, it turned out this was XYZ material, and then you can add that to the model. So you can actually make the model more complex over time. Whereas with the other systems, you've kind of picked all your filters, you've picked the hardware in advance, and you're sort of limited to what was put in at the very beginning. Whereas with this more rich data source, you've got this exquisite detail, there's a lot more that you can do with hyperspectral imaging. Okay, that's what I wanted to say about systems. So I'll pass this back to Olga now. Thank you.
Thank you, David. Let me just try to figure out how to share this. Okay. I think I'm unmuted and visible. So, so this is really just a summary of what David talked about. But benefits of hyperspectral technology is really that that we can detect a wider range of contaminants, not just based on color and contrast, but we can actually identify these contaminants. And we can do more things than that. We can assess quality of the product, and we can learn over time and improve inspection outcomes over time. So really, we're future-proof. If you choose to change your product setup, or new materials are coming in because new conveyor belts are available, you know, we can start adding new materials, new products into our database and be able to detect them. Again, the very kind of coming back to comparing to humans, all automated detection systems allow you to see things continuously at the same levels, so vigilance doesn't drop. And again, super important aspect to think about as you're looking at which detection system makes the most sense. And I'll give you a bit of a technological overview in a moment. So this is, you know, people are really influenced by a lot of things around them, whereas automated systems are not. They really depend on something like as simple as the location of the foreign object or the thing that you want to measure, and the speed and amount of material online. Everything else is taken out of the equation by automating inspection and detections problems. So just to give you an example of what we are able to do, there is actually a foreign object located in this bunch of bacon bits, and these were imaged at line speed. I believe this was running at around 100 feet per minute on our conveyor belt about 3 feet wide. So this is actual example from a working system online. And there is a small speck there. You can see it when you actually zoom in. But what's really interesting for us is not only that it was detected and found, please note that there are no false positives. And that is extremely difficult to accomplish in any detection system. And again, because we have so much rich information, for us it's easier because we can look at so many different color bands. The other work that we've done is tenderness measurement. And again, now we're looking at the larger area of the steak, and we can predict how tender it is as compared to shear force measurement. We're doing similar work on chicken. And again, you can see how complex and rich the information that we collect is. And finally, this is measurement of composition of bacon. And as you can see, actually, infrared light penetrates lightly into product. So we can actually see not just the surface composition, but we actually see product composition because we collect a couple of millimeters of information through each product. So what are other inspection methods, and do we think that hyperspectral should take over the world? Absolutely not. All systems have their place in a plant. For example, X-ray systems are very well understood, and huge advantage of X-ray systems is that X-rays penetrate through products extremely well. By now, safety of X-rays is well understood and well under control. The problem is X-rays still see mostly very high density materials. And if you have objects like plastics of low density, they're almost impossible to see with X-rays. So they penetrate and are fantastic for very dense objects like calcified bones or metals, but they can't see detailed chemistry and do fall flat when looking at plastics or wood or other organic contaminants. For example, bugs. Metal detectors, again, fantastic technology for finding metals. And, there is nothing better than a metal detector if something, an auger or something falls apart and you start seeing metal shavings in your plant. The problem is it uses a very specific method to find metals, so conductivity. And if there is a metal that doesn't conduct, like a non-ferrous metal or worse, stainless steel, metal detectors will not find anything. And the problem is salt, for example, added into your product changes conductivity of the product so much that you can get a lot of false positives. So again, not very specific, but very, very sensitive equipment. Camera systems, this is, David spent a lot of time on this, but super inexpensive, easy to use, but have some limitations where it is surface mostly, and is very, very difficult to look at low contrast situations. It's also provides more information than something like a metal detector. So analysis is very complex, and finding edges and location of objects is difficult because there is a lot of information, but it's not very specific. This improves with multispectral systems, where they can start looking at specific materials. They're more specific to those materials, but the problem is that they're tuned to a specific chemistry. Again, hyperspectral is very, very new on the market. It still has to grow into its own, but like camera systems, very easy to use, very safe. However, it does provide a lot of information. And I think the challenge is for a lot of the traditional imaging systems, the amount of software that we have to develop and the amount of algorithm development for hyperspectral is absolutely huge. So for example, PPO's hardware team is now smaller than the software team. And what we anticipate as this product really penetrates the market, the software analytics and helping our customers find what they need to find will be a really primary objective of PPO. So we look forward to further discussions on that. So again, kind of comparing, this is now finding foreign objects on bacon. There are foreign objects here. You can see some with the eye, but really there were a couple of cardboard pieces hiding and were not possible to find with any other method, including human inspectors, but are found with hyperspectral imaging. So we're very, very excited to have you here on this at this talk, and I hope that we kind of reduce the mystery of what hyperspectral imaging is and what vision systems are. The technology is coming to its own. It has been used in many other areas in medicine. Most imaging technologies tend to start in medicine, but we're seeing the development of new detectors, better algorithms, really has made this technology super powerful for the food processor. And we really look forward to talking with you, help you select the right technology for the right use in your plants. So with that, I will stop the presentation and then pass the baton over to Heather so she can maybe post some questions.
Awesome. Thanks, Ola. So for those of you who are on the call, thank you so much for being with us. If you'd like to ask a question, you can just use the Q&A button, which is down in the bottom band of your screen. So it should show up as a Q plus or Q and A. You just click on that and you can type in a question and feel free to ask. So I can see one coming through here, which I think maybe David might be best equipped to answer. David, if you want to unmute and turn your camera on, which is, can you explain a little bit about how the system learns? What does it do, and help us out with that one a little bit?
Sure. I mean, I don't think I can turn the camera on. If you've got it off at your end, it's not giving me the option.
Here, let me give me the, okay, I've just said ask to start video, see if it'll come.
Yep, there we go. Okay, that's
okay,
right, thanks. Sorry, the question was, how does the system learn?
Yes.
Yeah, okay. So I can say a bit about this. I mean, I think the topic of the next webinar is going to go into a lot more detail on this, but so the basic idea is, at least in our case, the way that we do it is we start off by, we have a whole room and a whole application, a whole cold room, and a prototype not a prototype, a kind of test system that we run in the back, which is similar to the one you get in the factory, that we run examples of the types of materials, the types of product that you've got. So for example, we'll run hundreds of pounds of chicken across the conveyor belt and we'll scan it with our system. And then we'll run materials of the type that the customer typically has told us we have problems with these 6 plastics or whatever that they're most interested in, or cardboard, whatever. And so we'll literally just spend hours running examples of all those types of material through the system and different realistic configurations, and then we'll label it and say, so we'll run hundreds of examples of say white cog rubber, and we'll tell the system this is what white cog rubber looks like. Whenever you see a spectrum that looks like anything under this pixel, that's white cog rubber. And so this is kind of the initial way that we build the models, just by showing it lots and lots of examples, and then we spend a lot of time testing how well that model works. So we'll create a realistic situation where, like several of the pictures that Ola showed earlier, showing like examples of big batches of bacon bits with real small pieces on the product. We'll run huge grids of this, of different size materials, etc. And we'll look back at it and find out how many pieces did we put in, how many did the system actually recover. And then we'll use that to feed back and train it more, saying, oh, you found too many false positives, or oh, you didn't find enough true positives. Maybe we need to put the material in a slightly different situation. Maybe we need to get more chicken goop over the top of it, or maybe we need to get the product wetter. Maybe we need to do other things. And we'll do this to refine the model over time. And then that's how we get to an initial model. And then we actually, the real bit where it comes into its own is once we get it into the factory, we'll then refine it further. So for example, the installation that we've just done recently, we had pretty low false positive rates. But once we got actually into the customer's factory and ran it, it wasn't working quite as well as it was in the lab. But as soon as we, like, just by being online and getting real chicken running through the system for a few minutes, we saw thousands of pounds of chicken going past, and we could actually feed that back into the system and say, no, this is actually pure chicken, there's no contaminants here, and refine the model in time and use that to tune how it's set between, as Ola said, everything is a balance between detecting true positives where you know there are things there and you don't want to miss them, and detecting false positives where it's just way too sensitive and thinks everything is a foreign material. So there's a lot of kind of this iterating that we do, but that's the basic idea. We show it lots of examples which we label, and then we test it and test it and test it, and then feed that back in and refine the model and then test it some more.
Awesome. Thank you, David. That's great. Yeah. So we have another question that's come through. How does the temperature of the product affect foreign material detectability? I think, Olga, that one probably fits with you.
Sure. So that's actually, it doesn't really affect the detectability very much unless we start seeing chemical changes. So for example, layer of ice might affect it a little bit. So we will, if that's something that's expected in a plant, we will actually run that through training, as David described. What does affect detectability is actually the temperature of the detector. So let's say your plant has huge fluctuations of temperature inside of it. The high temperature situation, if our cameras are not cooled sufficiently, might introduce much more noise into our system and therefore affect the detectability. So it's more the detector temperature that affects detection, not the object of interest or what you're imaging that is that important.
Awesome. Thanks, Olga. Do we have any other questions from the floor? I'm not seeing any come through, and I know we're getting close to time. So I think, Ola, I'll ask you if you don't mind just to pop up the last, I think there was a slide that mentions, and for those of you on the call, we will have another webinar on May the 29th at 11 a.m. So you'll see some details on that coming through with your wrap up
Sorry,
in 24 hours or so. We'll also be sending out a survey to everybody. So I hope you'll give us a little bit of feedback. This is our first webinar, and we are planning to do a series. So we'd love your thoughts on what we can do better, what topics you might want to hear about, and so on. So please do feel free. Oh, you know what? We've got one more question that's come through. I'd like to answer it. Oh, now two. So if everybody's willing to stay another second, we'll let these ones get answered. So the first one is, how does your equipment stand up to sanitation and cleanup? So Ola, do you want to take that one?
Sure. So actually, that's a fantastic question. And we do have a video on our website to show that. But primary design for our system was actually, how do we make sure that this technology works in the food industry? So if I actually scroll back to one of the recent slides, you can actually see that we have all stainless steel components. Everything is removable, access points to clean between conveyor belts and under conveyor belts are very easy to reach. So again, we have paid a tremendous amount of importance to how this system operates in the plant. So we're happy to give you more information on that, but there is a video showing the aspects of the whole gamut of work that we put the system through before it's shipped to a facility.
Awesome. All right. And the questions are now coming through. Okay. So next one is there a break in the background material and that is the contaminant? If there is a break in the background material and that is the contaminant, will it pick that up or just assume it is a gap?
Well, it depends on what you're looking for. We can, what's nice about our system, it's hyperspectral, but it can also behave like a vision system. So if that's one of the tasks that you ask us to perform, yes, we can actually find, broken shapes or unusual shapes or something that doesn't look normal, and we can start making you aware of that. But again, that really depends on what the tasks are that you give us to perform as we're working on the system for you.
Awesome. So two other questions here. The next one is, are hyperspectral X-ray and metal detector able to be combined into a single detection system?
Eventually, yes. Right now, we're not doing that, but certainly adding more detection capability into our system is something that we're looking at all the time. So if you ask the same question in about 5 years, I'm sure the answer will be yes. Right now, that's not what we're pursuing. However, we do recommend, for certain applications, having all three types of systems in line is very advantageous. And again, we would never claim that we're the silver bullet and we can solve all your problems.
Awesome. And one final question. Can the system detect material on both the top and the bottom of a product?
Yes. So again, if you look at the slide that I think I'm sharing, but maybe I'm not.
I don't see it.
Okay, sorry. So again, you can see a couple of videos on our website, but we do have several configurations which allow you to look at multiple sides of the product. One of the most versatile configuration is what we call a Z config, where we have two imaging heads in a system. We look at the top, flip the object or the product, and look at the bottom, which is now the top of a conveyor belt. So we do look at the both top and bottom of products. There are other solutions as well available, but the Z config is kind of the most versatile.
Awesome.
So I know, Heather, you wanted to say something, but I really wanted to say something. I see Wanfra is on the call, and we just wanted to congratulate you on the new addition to the family, Wanfra. And there is a onesie in the mail for you with possibly a PPO logo. So anyhow, but awesome to have yet another addition to the family here. So Wanfra, congratulations, and we need more pictures, please. Okay, Heather, I'm done.
All good. Awesome. And we're right on time. Thank you so much, everybody, for attending today. It was very much appreciated. We'll look forward to your feedback. If you have other questions, feel free to reach out to any of the sales team or others that you might know at PPO. And we'll make sure you get the information on our next one on May the 29th very shortly. Thank you so much, everyone. Have a great day and stay safe and healthy. Bye for now.